Welcome, my fellow assassins, to this explanation tutorial demo. I don't know what we're calling it, but in this episode or video, I wanted to take a look at string copy or strcpy in C. Now, strcpy, if you've been around the C world, gets a very bad rap, rightfully so in some regards, of being very prone to things like buffer overflows. And it's not the only function in C. There are others like sprintf, scat, or strcat, etc. But like if we go to the man page of strcpy here, you can clearly see there's a it basically tells you that you should not be using this. Notice here, beware of buffer overruns. So yeah, it's basically kind of common practice that you shouldn't be using strcpy specifically because of that reason. But with that said, I do want to show you how you can actually use strcpy safely and not have to worry about buffer overflows. And I wanted to do that with a bit of an example, but to really drive home the point as to why strcpy and the subsequently similar functions are so bad, I wanted to actually perform a buffer overflow for you right here. So I have some code pulled up here, just a pretty basic function right here, just some pretty basic code. So this is, of course, where our buffer overflow exists. It's these lines right here. We have just a fixed size buffer right here of 20 bytes, and we're copying this random data value of an unknown size, copying it directly into it. So as you could see, that would easily cause a buffer overflow. Now, basically, all of what this program does is it reads in a file here, and then it puts that into data, and then assuming that we actually read the file successfully, then it pumps it into this is uchar a string, and then it basically prints if it's a string or if it's just binary data. So pretty simple for the most part. So if we go over here and we go to run this, so we do make main. I already compiled it. So if we do main and then we pass it in, say, a test file, we can see it works just as we expected. Now, of course, this test file just has a few A's in it, so of course this isn't going to overrun the buffer. But if we use a little bit of a longer file, so we do main long file. Here we're going to see some interesting results, right? We see this segmentation fault core dumped. And the reason why that happened was, of course, we copied in more data than what we had allocated, and we overran the buffer, caused a buffer overflow, and we basically caused the program to crash. Now, if I run this bad file that I created, we're going to see this interesting print here. This should never print. So what exactly is going on here? Well, this is actually an exploitation of the buffer overflow. Now, what I didn't show you in the code over here is I put in this extra function called secret, and here we can see that this function clearly says this function should never print, because if we actually look through the code, that function never gets called anywhere, yet we can clearly see in this output that it did in fact get printed. So what's going on? So in order to kind of understand why and how this is working, what we should probably do is kind of get under the hood of this program. So what we can do is we can go into GDB here for main, and this will kind of bring up the debugger here. And then what we want to do is we want to put a break statement right here at line 59. So what we can do is we can do B59. So then once the program gets to line 59, it'll basically pause execution. So let's run our test file again. So if we do run and then test, that'll use our test file as input. And then there we can see we got to our breakpoint. Now what we can do is we can basically dump what the contents of the stack is. And here we can see some interesting input here. So we see these 61s. So the reason why this test file I did a bunch of A's is because the ASCII value for A in hexadecimal is 61. So we can basically really easily see where our input is in the buffer. So what we'll notice is this value right here is actually our return address. Now, the way we can figure that out and way we can confirm that is if we do a dis main, so this will basically disassemble the main function. And what we can see, so this is our function right here that we're going into. And then here we can see the return address is 54 CE. And again, we can see here this is 54 CE. So that is our return address. So that's how we know where to overwrite the return address as we're overflowing our buffer in order to create this buffer overflow. Now, how do we know where to jump to get to this secret function over here? Well, because we know the secret function exists, we can do the same thing, dis secret, and that'll print out where the address is. So essentially, we just put this return address here in this spot up here, and that will basically cause the program, when it gets to the time where it's time to return from that is uchar stir function, it will, instead of jumping back to where it's supposed to, it'll jump to our return address, which happens to be the secret function. Now, one thing that if you didn't know, if, like, say for instance you didn't have the source code here, one thing that you could do in order to check to see if this if there's anything else in this file, so we can go ahead and quit out GDB here, clear the screen. If we do an object dump and then -d for disassemble, and then the main, which is our program. So here we basically get to see all of the assembly of our program. And if we scroll up a ways here, so there we can see our buffer overflow susceptible function. And then if we keep going up a ways, we will see that there is this secret function. So that's another way that you could figure out that this secret function exists. So as far as crafting the buffer overflow itself, I have a just a simple C program here to basically create the bad file for us. So it's fairly simple. So we basically just create the size. This offset, this is so if you actually calculate it out, this is basically 40 bytes in hex. So that's basically where from the start of the buffer to the return address, like how far basically is the buffer to the return address. And then of course here we can see that same return address here that we wanted to jump to. And then this basically just creates the file for us and then closes it out. So that is all good there. And then of course we built that, ran it, and we got our buffer overflow. So if we run it, we can actually run it again with their bad file, and there we get it again. Now, one thing I should mention too, if we go to the make file here, one thing I am doing is I'm basically disabling everything that's in place to prevent buffer overflows, and basically making this as simple as possible, purely for the academic purpose of showing you what a buffer overflow can do. Now, the other thing I also did was disable address space randomization. So basically in like Linux, so I'm in Linux right now, what the kernel will do is basically every time your program runs, it'll randomize its stack space in order to prevent, buffer overflows just like this one, where you hard code the values in there. But purely for simplicity's sake and for repetition's sake for this video, I just kind of disabled all that stuff to make it easy. But it goes without saying that you can very much do get the same exact output with a buffer overflow with all those protections enabled. I'm just, like I said, disabling it just for simplicity's sake. So if we quit back out of that, so now it comes to the question, how do we actually fix this buffer overflow? Now, of course, the most simple solution would be to use something like strcpy to basically only copy in the requisite data. So for instance, if we did if we just change this to strncopy, and then we did the size, say 19, so one less than temp there, and then we quit out of this. Actually, we didn't need to quit out of that. And then we go to make main again, and then if we do main on the bad file, we can, of course, see that works as we'd expect, and we don't have any sort of buffer overflow. In fact, if we go pipe it through valgrind here, do main, bad file, what we're going to see is everything works as we'd expect, no memory errors, no nothing. So that's basically what we want to see. But that's not what we wanted to do here, right? We wanted to do this with strcpy and how we can do it safely. Now, probably at least the best way that I can think of is do basically something like strncopy. And basically, essentially, what that would be is to take in a size. So we can do size t, call it size. And then instead of hard coding this, which you technically could just do this, but it's generally bad practice to do that just because, and depending on which C standard you're in, you might not be able to do that. But the reason why you don't necessarily want to do this is because the stack size is limited. So for instance, we're reading data in from a file. So if your file is absolutely massive, there's a chance that you could take up more memory than the stack has and crash the program that way. So it's best to just kind of allocate this on the heap. So the way that you would do that is, so we'll just actually get rid of this here. So we'll do char temp. And then because we want to just initialize everything to 0, we can call calc. And then we can pass in the size, which is the size. And then this is going to be a size of a char value. And then, of course, we want to actually make sure that that worked. So if temp is equal to null, we know that that failed. So we can return 0 because 0 means false. And then, so if it succeeded, we know that we can do a strcpy with the temp, and then we can do the data. We don't need this 19 anymore. And then, of course, because we want to free our memory and be good programmers, well, what we can do is go up here, ret 0, and actually we can just make this ret for simplicity's sake. And then what we can do is we can do ret is equal to is alpha, and then temp 0, nope. There we go. And then here, this of course is just going to return ret. And then of course, above that, we will want to call free on our temp value. Just like that. So that looks pretty good. So again, what we're doing here is we're taking in the size coming into the function, which should be the size of data here. We're allocating that memory, setting it all to 0 with calc, checking to make sure we actually got the memory we requested back. And then we're calling strcpy to copy that data into temp, checking to see if the first character is an alphanumeric character. If it is, or I guess just an alpha character like A through Z. If it is, we basically store this as a return value, free our temporary variable, and then return our result. Now we will have to make one more change down here because of course we added another variable. We'll have to go in here and pass in the size. And as you can see here, we're setting the size as an output parameter here in this load file function. So that looks pretty good. So let's go ahead and try and compile it and see what happens. And of course we have some errors because of course we do. If I actually knew how to program, this would be actually size up, not size. Run make again, and there we go. That worked good. And then if we do main on our bad file, we can see it works fine. Main on our long file, that also works fine. If we do valgrind main bad file, we can of course see we have no memory issues, and we have an additional allocation here, of course, because we did calc some memory here. So yeah, that is how you can go about using strcpy safely without having to worry about buffer overflows. Now, while this is, how to make strcpy safe, this is what you should honestly be doing for all of your C programs when you're copying any data into a buffer. It doesn't matter if you're using strncopy or strcat or any of those other ones. You always, always, always want to make sure the data going into your buffer your buffer is at least as large as the data coming into it. So you always want to be doing those checks. And here we can see in these lines here, we are doing those checks. So we do know that temp is going to be large enough to receive this data. Now, of course, actually one thing I probably should have done here is, instead of doing size, just to be on the safe side, do something like size +1 just to have like a little extra. But suffice it to say, we're making sure that we have enough data allocated for this strcpy. So this also begs another question of, okay, so we have this, extra size here, but does this actually prevent a buffer overflow from ever happening? In our program here, yes, it does. Globally speaking, not so much. So let's say hypothetically we wanted to create a library with this function. It is feasibly possible that a buffer overflow could still occur. And basically the way that would happen is if someone passed in some data and a size and they weren't correlated, or the size was too small. So for instance, if data was, say, 40 bytes long, but they passed in 20 for the size, in which case, yes, this could still cause a buffer overflow. But then again, it's the same thing if you used strncpy just in reverse. And what I mean by that is, so strncpy basically goes up to the n value, or the number value. So as we demonstrated earlier, we put in 19. So basically what strncpy would do is it would copy up until it gets to the null terminator value, or essentially a 0. And then or it goes to the length. So in our case, it got to the length of 19, didn't find the null terminator, so just stopped. But if you put in a value that was too large, so rather than being too small causing a buffer overflow, you put in a number too large that causes a buffer overflow, theoretically, you could still achieve a buffer overflow in that regard if your buffer that you're copying into is smaller than the data coming in and there's no null terminator in the data. So I guess to demonstrate that real quick. So basically what I'm saying here is, if say you have a buffer with, say, 1, 2, 3, 4, 5 spots in it, and then you're taking in data that has a lot more than that. But the size you give to strncpy is only, say the number you give for strncpy is, I don't know, like 13. Of course, 13 is greater than your 5 here, so you're going to copy in more than what your buffer can handle, and you'll still have a buffer overflow. Just potentially the damage is going to be reduced, because by having that upper limit cap, it kind of limits how much the attacker could overflow your buffer. So in our case, we saw 40 bytes was what got us to the return address. So even if you did something like this, at least in this specific example, you still wouldn't be able to overwrite the return address. But of course, it's still not good if you're overwriting memory. So yeah, that was how you can make strcpy safe and how to use it effectively. So I hope you learned something in this episode, in this video. And if you did, definitely be sure to leave it a like, comment, and subscribe if you haven't done so already. And I will see you in the next one.